Good afternoon, and we will be starting a new section today. This is called MultiWay trees. If I am not mistaken, in your book, this is in, whoops, let me select the right tools here. Please bear with me. There we go. This is chapter 10. And I believe the topic here, it's called MultiWay trees. And we're going to discuss two different kinds of them. There's something that's called a 2-3-4 tree. And there is something else that's called a 2-3 tree. And we'll get to both of those a little bit later. What I wanted to do here, I wanted to give you a little bit of motivation. So you could call this particular video, this is an intro. My pen seems to be skipping a lot. I don't understand why. An introduction, or this could also be called motivation. Might even be a little bit better name for what we do here. Yeah. And what I want to do is I want to go back to the database assignment that you've been working on this semester. 3 of your 4 programming assignments had to do with this. And you remember we have this big array here, this database array. And the database array is made up of a first name, and it was made up of a last name, and it was also made up of an ID. And what happened is basically as we were adding things to this database, again, I have a Skippy pen here, don't quite know why. We just kept the adding at the end. Basically, the idea was someone new comes in for insertion, they get added at the end. We had a couple of tricks here for maintaining a deleted list. That's not the issue I want to talk about here today. But then at the same time, and we did this 3 times this semester, we had these indexes, and we might have had a first name index, and we had a last name index, and we had an ID index, and these were kept in order. So that, in other words, if I came over here, this might be Al, and this might be Bob, and this might be Dave. And again, this corresponded to a particular record number. Record number being the index into this array over here of where we'd find this particular person, the person whose first name was Al. And we did this for access methods. In other words, if we wanted to see a listing of all of the people in this database, and we wanted them to be listed out by first name increasing order, we would come over to this index and we would first print out this record number, and then this record number, and this record number. And we did the same thing over here for the last name, and we did the same thing over here for the ID. Now, the usefulness of having these particular structures right here, these indexes, might not be so apparent from this example over here. But what I want you to do now is I want you to consider a more realistic example. So suppose I have over here, I have a database record. So I'm going to say a database record, but it's made up of a lot more information. And maybe it's made up of a first name, and it's made up of a last name, and it's made up of an ID number, and there might be an address, and there might be a city, and there might be a state, and there might be a zip. Again, I don't understand the problems with my pen here. And there could be other things here. There could be a hire date. There might be a pay grade. There could be a phone number. You get the idea. So the point here is that our database record might be quite large. Okay? And I have certainly worked with database records where this thing could be up in the thousands of bytes. So let's just pick a number here. Why don't we just assume that this is 1024 bytes. So that now when I go back to my original database, and I'm looking over here, and here are each one of my database records. Okay, and again, the whole idea is that the width of this thing is 1024 bytes. That's a lot of information. And now if I came over here, and maybe over here was my first name, and maybe over here was my last name, and maybe over here is my ID. And again, we maintain these indexes over here, whether they be ordered arrays or linked lists or binary search trees, F, L, ID. We can see now that when it comes over here, and remember what's going on here is each one of these records in here, these index records as we've called them, they're not that big, okay? Maybe we allocated 20 bytes for a first name, okay, 20 characters, and then we had a record number. And a record number, that's an integer in Java, that's 4 bytes. So this would be a total of 24 bytes. 24 bytes is a lot less than 1024 bytes. And what happened is we manipulated these data structures here, okay, to keep track of these things in order by these things over here. First name, the last name, the ID. Now it should become a little bit more apparent than in the examples we've been working with all semester, the advantages that these things give us. For example, suppose we wanted to keep this whole thing in order by ID number, okay? And suppose we're using ordered arrays. Well, over here, if I didn't have the indexes at all, okay, if I were to impose some sort of sorting algorithm on here based on this value over here, every time I'm swapping two records, remember I need a temporary one as well to swap any two of these, I would be moving around 3 times 1024 bytes. I'd be moving over 3,000 bytes. Whereas over here, if I'm using my insertion loop over here, I'm only bumping things down that are about 20 bytes. So I hope that you can understand that these things are now providing us a great savings in terms of the amount of data that we need to move around inside of the computer. And that is the motivation here for this chapter on what are called multi-way trees. Now, let me just do a few things here so that we can start talking about multi-way trees. So the first tree that we are going to talk about is this thing called the 2-3-4 tree. And the whole basis of the 2-3-4 tree is what does a node look like? And a node looks like this. And the thing is this is data. This is data. And this is data. And this over here, this is a reference. This is a reference. This is a reference. And this is a reference. Okay? So the basic idea of what's going to happen here, and we'll get into a lot of details here in a second. If we were to look at an example of a 2, 3, 4 node, and there's a 10 over here, and there's a 20 over here, this is going to be a reference to another node. This would be a reference to another node. This would be a reference to another node. Now the thing that I want to point out here is that the rules about 2, 3, 4 trees are as follows. A 2, 3, 4 tree, so we have references, and you can imagine that we have, the references is going to be an array of 4. And the data is going to be an array of 3. Okay, and we always have the relationship that the number of references is equal to the number of data plus 1. Now, in this particular node over here, notice that there are 2 pieces of data. So what that means is that there are going to be 3 references. If I had something over here with just like a 15 in it, there would be a reference there, and there'd be a reference there. If I had a node over here with a 20, 30, 40 in it, then there would be a reference here, 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 and here. Everybody get it? So the reason why it's called a 2, 3, 4 tree has to do with the number of references that you can find in a node. Here are 2 references, here are 3 references, here are 4 references. There is never a node with 0 data. Anytime there's a node, it has to have at least 1 data, and it can one piece of data, 1 datum, and it can have a maximum of 3, which means that I'm always going to either have 2, 3, or 4 references. So there is never a node with 0 data. And another thing that you should know is that the data is always sorted within a node. Okay, so you'll notice here it's sorted, you'll notice here it's sorted, you'll notice here that it's sorted. One thing that we're going to talk about here, and by the way, we're not going to be looking at any code on these things. This is a chapter that is all pictures, although there is code in your book, and I am going to strongly encourage you to look at that code. New data is always inserted in a leaf node. Okay, so with that out of the way, let's talk about how these things work. So imagine that I have, let's say I want to insert $30, 20, 40, 25 into a new tree. Okay, so initially the thing is empty, And I'm going to take some liberties here, and I think you're okay with that, that I'm not going to be formal and draw all these boxes. I'm going to draw my nodes like this. It just makes the drawing of these things a whole lot easier. So if I am step 1, I would have a node that just looks like this. And there'd be a 30 in it. And because I now need to have two references over here, that would point to null, and that would point to null. And now if I want to insert this, basically what I'm going to be doing here is I would use the insertion loop that we've used before. So now what's going to happen is I'm going to come over here, and I'm going to have to first shift over the 30. So the 30 is going to come over to here. And what's going to happen is remember, they're really these references here. This reference is going to get shifted over one. So this reference is now pointing here. And this reference is going to get shifted over one. So that's over there. And now I insert my 20, and I create a new reference. And it looks like that. And now I'm going to come over here and I'm going to insert 40. So I take what was there before, and again, the only thing that happens between here and here is I inserted the 40. The references didn't move this time. Okay, when I insert the 40, I have to do it here. Okay, so now here comes the big thing. I've got to insert this. And the rule whenever you encounter a full node, you must split it. And the question is how do you do that? And the answer is, so I'm getting ready to insert 25, and I come into my tree and I say, uh-oh, this thing is now full. The way that you split it is actually very simple. What I am going to do is I am going to take this node, or I'm going to take this value, 30, and I'm going to promote it. So I now have 30 over here. And what's going to happen is over here now, I've got 20. And over here, I now have 40. So the way that what happens over here, the way that we split a full node is we take the middle value, we kick it upstairs into a new node, and then it has two children, just like this. Now I get ready to insert the 25, and the 25 is, now first of all, realize of course this is a null reference here. This is a null reference here. Null reference here. Null reference here. And now I've come in here and I've put a 25 in there. And there's a null reference there. Okay? I want you to notice that at this point, the tree is even, okay? Or the tree is balanced, okay? And we're going to see that 2, 3, 4 trees stay balanced, which is a really nice property. 2, 3, 4 trees stay balanced. Nice property. So what I'd like to do now is I want to do a few more things here. Why don't we insert, let's make up some good numbers here. I'm going to say 8, 10, 28. Why don't we say 50, 60, 70. Okay? So what's going to happen over here is if I want to insert an 8, and let me see if I can do this. Let's see just how clever I can be. Give me a moment here. There we go. So I'm going to come down here. So I had, whoops, that is not what I wanted to do. I'll do this. So I had a 30 here. Okay, and over here, it was pointing down to a 20 and a 25. And over here, it was pointing to a 40. And I'm going to start to take some shortcuts here, but I think you'll let me. So I'm going to insert an 8. So I come over here, and I go down the 30 because it's less than 30. So I come down to here, and I see that there's room to insert it over here. So what I'm left with is 30, and over here, I'm pointing to a tree that is 8, and it's 20, and it's 25. And then I come over here, and this is pointing at 40. Okay, and now I want to insert a 10. Okay, so watch this. This is going to be interesting. So I come to the 30, and I'm going to go down to the left, and look at what's happened here. I have now encountered a full node. So I've got to kick the 20 upstairs. So what's going to happen now is over here, I'm going to have a 20, and I'm going to have a 30. And what's going to happen over here, the 20 got kicked upstairs. So over here is 8. Over here is 25. And over here is 40. Does everybody see what happened over here? The 20 got kicked upstairs, and then I had 2 children left. Okay, I have to go ahead and insert the 10 now. The 10 is going to go in this node right here. Everybody okay with that? Now I'm going to insert a 28. That's going to be easy. I come over here, and it is between 20 and 30, so I come down here. The 28 goes here, like that. I'm going to come over here. I'm going to insert a 50. The 50 is going to go over here. I'm going to come down here. I'm going to insert a 60. The 60 goes over here. So this is what my tree looks like now as I'm getting ready to insert the 70. Okay. So over here, remember, this is a node here. This is a node here. This is a node here. And this is a node here. Okay, so that if I'm getting ready to insert a 70, okay, I come over to here and I go, well, I've got to follow this branch down here, and I've got to come over here, and now what I'm going to do is I'm going to have to kick the 50 upstairs. So when I kick the 50 upstairs, I've got 20, 30, 50. Over here is going to be an 8 and a 10. Over here will be a 25 and a 28. Over here, okay, now because I kicked the 50 upstairs, over here is going to be a 40. And over here is going to be a 60. And remember, my goal here was to insert a 70. That would go in over here. So I want you to notice a couple of things. It's still balanced. How cool is that? Okay, and just to have a little more fun here, because I think you're getting the idea, why don't we insert another value? It really doesn't matter what the value is. Let's suppose I wanted to insert 29. So I come over here. Remember, I'm going to have to maintain a reference to the top of this thing just like that. Now I come over here, and remember, I'm on the way down, and I've already encountered a node that is full. So I've got to go ahead and fill it up, or split it. So I'm going to come over here, and I'm going to get a 30. And let's see, to the left of the 30, I am going to have 20. And to the right of 30, I'm going to have 50. And from the 20 over here, I get my 8 and my 10. And I am coming over here, and here I get 25, 28, and now, by the way, I can insert my 29. So it goes there. Now, I don't split this now. I only split them when I encounter them on the way down. I come over here, and here is going to be my reference to the 40. And I'm going to come over here, and I've got my 60 and 70. And look at that, it's still balanced. Very cool. So I'm going to leave it as an exercise now. And I'm going to say insert. Well, let's make a few interesting things happen. So here's 25, 28, 29. I'm going to say insert a 26. So that's going to cause a split. I'm going to come over here, and I'm going to say, why don't we insert 80? And then why don't we insert 66? And that's going to do it too. So I'm going to leave that as a homework exercise. And I'm going to create other homework exercises for you. But I want to go back to something else now, because we've talked about how to insert. The other question is how would you search? So for example, suppose I'm given this tree over here, and I'm asked to search. I'm asked to search for 28. Well, what I would do over here is I would start with this node, and remember what I've got inside of here, this is a sorted array. It's not a very big sorted array, it's only an array of 3. I think doing binary search on it would be a bit of overkill, but I would basically I would do a linear search, and I would just say that while I'm referencing something that is less than this, advance it. So the question is 20 less than 28? And the answer is yes. So I would go ahead and say I'm going to advance the reference now. And the reference would be over here. And then I would say, is what I'm looking for less than this? And the answer is yes. Now, the answer is yes, so that would suggest to me that what I need to do now is I need to go down here and repeat the process all over again. If the answer is no, then what I need to do is I need to ask, does this equal this? So basically what I could be doing is if we call this the key, okay, and you can think about it this way. I think I need one more space here. Ah, look at that. I'm all out. Do you all like my cat? I am going to come over here. I'm going to say File, New. Okay, so I've got a node here. And my node looks like the following. Here's reference 0. Here's data 0. Here's reference 1. Here's data 1. Here's reference 2. Here is data 2. And here's reference 3. And we can imagine that this point somewhere, this point somewhere, this point somewhere, this point somewhere. Maybe this has the number 10 in it, 20, 30, and I've got some value over here, key, and maybe key is 15. So what you might be doing is you might be saying something like the following: while I might come over here and say let I equal 0, and I might say something like the following: while data of I is less than and equal to key, and then you got to do something like this, and I is less than, and remember, there may not be 3 elements in here. I'm just going to put a question mark in here. I'll leave it to you to fill that out. And what am I going to say? I'm going to say something like I plus plus. So, in other words, I come in here and I go, is data of I less than or equal to key? Sure, I'm going to go I plus plus. And I'm going to go, is data of I, so I'm over to here now, and I go, is data of I less than or equal to key? Oh, I'm sorry. While data of I, while this is less than the key, go up to, okay. So we would stop over here when I is equal to 1. So then the question that you need to ask here is does data of I equal key? And I'm going to say, if yes, found. And I'm going to say, if no, then what do I want to do? Well, then at that point, I want to follow this reference down. So then I'm going to say, search reference of I. Okay. In this case over here, data of 1, we're going to exit this loop when I is equal to 1. It turns out that this doesn't equal that. So what does that mean that I should do? It means that I should now follow this reference down to another node and start searching there. If it turns out, if I finally get down to if it turns out that this is null, then of course I haven't found it. Okay. And that's how I would do search. You will notice that we haven't talked about delete. No delete here. That's a complicated problem. Even your author decided not to talk about it. And that's basically it for 2, 3, 4 trees. And it's not going to take us much more to talk about 2, 3 trees. Okay, I'm stopping the video for a moment.